Okay, so this example problem is 11.124. Again, I'll read it to you. A bus starts from rest on a 200-meter radius curve and accelerates with its speed increasing at a sub t, the tangential acceleration, 2 meters per second squared. Determine the distance and time that the bus will travel along the curve before the magnitude of its total acceleration is 3 meters per second squared. Okay? So let's write down the givens. We're given that the, did I get that right? Yeah, starts from rest, okay. We're given that the initial velocity of the bus is 0. Of course, this would be its tangential velocity. Radius of curvature rho, 200 meters. And tangential acceleration, 2 meters per second squared, because they told us that the velocity was increasing at a rate of 2 meters per second. We know that the magnitude of the final acceleration is 3 meters per second squared. Why did I write it this way? Well, I wrote it as a vector to show you I'm trying to take the magnitude of the vector, because you realize that the bus will be moving on a curved path. Let's draw that while we're at it. So here's a curved path. The bus starts here. I'll just draw it as a particle. It begins with no velocity, but ends up accelerating and having some tangential velocity, but it's moving around a curve now. So now it continues to accelerate in the tangential direction. It's now accelerating in the normal direction since it has a tangential velocity. And so it's the vector sum of these two that is 3 meters per second squared. The question is, how long does it take? Let's put the find over here, I guess. How long does it take for the bus to reach a total acceleration of 3 meters per second? And what distance does it accomplish in that time? Now, this distance that it accomplishes will be the distance along the curved path. Okay? So those are the two things that we want to find. All right. Now, there are two ways to work a problem. There's what I call the bottom-up approach or the top-down approach. And I try to work problems both ways to give you an example of each. When I say the top-down approach, what I mean is you begin with what is asked for, you find an equation that relates to that, and you try to use it to go back to plug in what was given so that you can solve for it. The bottom-up approach is just to take what you're given and try to expand it into an equation. Try to take it and put it together, try to put the puzzle pieces together in some way to end up with an answer. Okay? So what I'm going to do here is go from a bottom-up approach. I'm not going to begin with what I'm trying to find. I'm going to begin with what's given and see what I can do with it. It's kind of like playing with the problem just to see what you can find. So let's begin with this. We know that the final acceleration will be 3 meters per second squared, and that will be a vector sum of AT and AN. So let's write it that way and see what happens. So the magnitude of the final acceleration can be written as the square root of the normal acceleration squared plus the tangential acceleration squared. Okay? But I know that the normal acceleration can be written as the tangential velocity squared divided by the radius of curvature. Be careful here. Don't let your brain confuse you on these two squares. They are two different things, okay? This is just the normal acceleration. I have to square it to get back to this point. Okay? So plus tangential acceleration squared. Okay? Now, this seems to help a little bit because I essentially have this side, it's 3, but if I only had the tangential acceleration, which I do, and the tangential velocity at this final point, then I'd be doing pretty good, right? Things would work out. In fact, if you look at this, I'm not really interested in the velocity, but I could get it at this point, right? Because the velocity is the only unknown. So at this point, I can go ahead and solve for that and figure out how fast the car is moving at this time. But what I really would like to find is time. So let's play with this a little more. we know that the tangential acceleration is 2 meters per second. I won't write the units for this equation, but you also know that the tangential acceleration is the rate of change of the tangential velocity with respect to time. So you could integrate this equation and say, well, let's see, the integral from rest to time t of 2 dt, what I've done here is I've skipped a step. I moved the dt to the other side. Okay, so it's 2 dt equals dv dt, or dv of t, equals the integral of this numerator, which would be d, if I can make a decent d, vt, and I've got to evaluate between the same limits. Well, the bus begins here with no velocity, so the tangential velocity is 0, and finally it has some tangential velocity, v sub t, at the final point here. Okay. So what does this mean? Well, if I integrate both of these are very simple integrals because I'm just integrating the differential of two variables. So I end up with 2 times t evaluated from 0 to t equals the tangential velocity evaluated from 0 to its velocity at this point. This velocity, even though I'm using the same symbol, this velocity is the velocity along the path, the tangential velocity that varies. This velocity, I'm really applying it at the final point. So I guess I could put an F here for final, a not here for initial, to make it very clear that I'm talking about the tangential velocity at that final point. Okay. Anyway, this is straightforward because the zeros just basically drop out. You'd have 2t, and let me clarify one thing. This time is the time along the path, but this particular time is the end time, so we can put a t sub f there. Okay? So this would end up being 2tf equals vtf, and I probably made a mistake along the way because I probably should not have pointed to the final time as the time that I want, because really this equation applies along the entire path. You give me a time and I will give you a velocity, right? At time 0 the velocity is 0. At time final the velocity is whatever the final velocity is. Okay? So this is an equation that essentially relates velocity to time. So another way to write this would just be 2t equals v sub t, which is more general than what I've got here. Okay? So far so good? Any questions? All right, so basically I can take this and plug it in up here. I've gone through a bunch of calculus essentially so that I can get rid of vt and plug in time instead. Okay? So, how do I want to do this? Let's just do it this way. The magnitude of the acceleration then is the square root of 2t quantity squared divided by rho all squared plus the tangential acceleration squared. Okay? Now why did I do that? Well, the only unknown in the equation is time. So if I set this acceleration to the final acceleration, which is 3 meters per second squared, I should be able to solve for time and figure out the final time, which is one of the things we wanted to find. So let me move back up here to the top. I'll erase most of this. In fact, you'll have the video, so I'll just erase all of it except for the equation that I'm working with at the bottom. Okay, so let's plug in some numbers. I usually don't like doing that. I usually like to solve algebraically, but I'll just go ahead and solve numerically. 3 meters per second squared equals the square root of 2t quantity squared divided by the radius of curvature, which is 200 meters. Now, I'm going the wrong way on purpose, okay? I'm not plugging in units to show you a point. Okay. Plus 2 squared, because we know that the tangential acceleration is just 2 meters per second squared. So putting some of the numbers together, this is the square root of 16t to the 4th divided by 200 squared, plus 2 times 2 is 4, so let's just simplify that. If you square both sides, then you'll have 9 equals t to the 4th divided by 2500 plus 4. Solving this out, 5 is t to the 4th over 2500. And so 12,500 is equal to t to the 4th. And then you can just take 12,500 to the quarter power in your calculator. And this is about 10.57. But 10.57 what? Hopefully seconds, right? Now, it is in fact seconds, but notice the reason I don't like doing this is because once you just plug in numbers, especially with no units, you have no idea where those numbers came from. For example, this 9 came from the final total acceleration squared, but this 4 came from the tangential acceleration squared. What I ended up doing was subtracting the 4 from the 9 and got 5 over here. And that's fine, but I don't really know where this 5 came from without a lot of thinking and a lot of analysis. If I had left this in symbolic form and solved for time by itself, then I could see where all of the stuff comes from. Yes?
Where did you get a 2500 from?
The 2500?
Yeah.
Let's see, 16 over 200 squared. Good question. Anything else? And that kind of proved my point, right? Where did the 2500 come from? Well, it's a couple of numbers I plugged in. It would have been better to leave it separate. Okay? Now, for the sake of the video, I'm going to solve it again and solve for t algebraically. Okay? I don't have it on the sheet, but at least you'll have it on the video. So let's do that and see if this makes a little more sense. What I would probably do is simply square both sides. So I would have the total acceleration squared in the final case equals, and then simplifying this is actually pretty straightforward. 2 squared is 4. T squared is just t squared. Then you'd have 4 squared again, which would be 16 t to the 4th divided by rho squared, because the square for the rho would come from here. Now this 16 is not really a problem that I have a 2 there. I did lose something along the way. I don't remember what it was, but the 16 will end up having units because we really need 2t to have units of velocity, which would be meters per second. So 2 must have come from the tangential acceleration. So this 16 would have units of meters squared per second to the 4th, if I'm thinking right. Let me check real quick. We ended up with 2t equals vt. So since we have meters per second here equals seconds here, then that 2 should have units of meters per second squared. Yeah, so that would work out. So that 2 has units of meters per second squared. So when we square it twice, let's see, meters, am I thinking right? Meters per second squared, we square it, we get meters squared again, we get meters to the 4th. Yeah, so this has meters to the 4th divided by seconds to the 8th, right? That should be right. And then we have time to the 4th power. Would that work? Let's see, seconds to the 4th power. Yeah, that would work. Okay. So once again, it kind of bit me that I didn't carry units to the entire solution. I had to go back and think hard to figure it out. Hopefully I've got it right. Now the tangential acceleration, I'll just leave like that. Let me get rid of this equation so I've got a little bit more space. Okay, I want to find this time. So to do that, I'll take the total acceleration squared less the tangential acceleration squared, multiply it by, okay, what I'd be left with is this term, so I have the denominator pull to the other side. The radius of curvature squared would be equal to just this numerator, 16 meters to the 4th over seconds to the 8th, multiplied by time to the 4th power. So then we have acceleration squared less tangential acceleration squared quantity, radius of curvature squared, divided by this 16 meters to the 4th per seconds to the 8th. That should be time to the fourth, but I don't want time to the fourth, so I'll just take the 1/4 power of all of this. Let me erase some of this so that you can see it. So there's the solution. Okay? And now I can see where everything comes from, and when I plug in numbers, I can verify the units as I go and make sure it comes out right. And I already know it's correct, so I'll just put seconds here and leave that as an exercise to you. It's a good exercise to try and plug in the units here and see if it works out for time being in seconds. Okay? So 10.57 seconds is the amount of time required. Now, let me give you what initially will sound like discouragement, but finally will be encouragement. Okay? On my exams, when I give you a problem, even something as simple as this, you see how easy it is to make a mistake. What do you think the probability is of you getting the right number on the exam questions? They're pretty low. They really are. Okay? Now, how am I going to give you credit? And am I going to just look at the number? No, I can't do that, right? I'd have to fail everybody. I don't want to fail everybody. I want to give you credit for what you've learned. So what I do is I study your answer. I look through it, and I try to figure out what it is you know and what it is you don't. And the things you know, I give you credit for. If you have some really boneheaded mistakes that are really bad, like not using units at all, or working in SI and suddenly just writing down a unit in English units, then I'll probably take some points off for that. But generally, I just try to give you points for what you know, okay, what you've learned in the class. So when you're solving the exam, be sure to go through every step. Don't assume that I know what you're doing. Write down everything, because the more you write down, the higher your chance of getting scored. Okay? Not only that, but you show me more of what you know, and I can give you credit for what you know then. Okay? Remember, don't just try to rush through and get a number at the end. That number is probably going to be worthless. Okay? Unless you get lucky or you're really, really good, you're probably going to get the wrong number. Okay? Now, that sounds discouraging. What's encouraging is that I give you partial credit. So just show me everything that you think, and I'll give you as much credit as possible. Okay? Let's finish this thing off, and then I'll let you go. Okay, so the last thing we need to find is how much distance is accomplished. So let's do that next. Notice that the tangential velocity is the change along the path with respect to time. Now, this kind of bends your brain a little bit, because so far you've been thinking about velocity as being something that has a linear position change, something that's in a straight line. But why couldn't we write that the tangential velocity is the rate of change along the path? You actually can. It's the same thing. It doesn't matter that the coordinate, S, is a curved coordinate. It still works. Okay? So, if this is true, then we can say, and by the way, the velocity can be written simply as 2 times time. Then we can integrate this equation, once again separate and integrate, ds equals 2t dt, and this is a very easy equation to integrate. So integrate both sides from 0 to s ds, in other words, from the starting position to the final position. Of course, this equation would work along the entire length as well, equals the integral of 2t dt from 0 to t final, okay, when we reach this position. And so, s, which is what we get from this whole thing, this is just a complicated way of writing the distance delta s, or the distance s we go from the initial position, is equal to the integral of 2t dt. Now help me out. What rule that we've already written tonight are we going to use to integrate 2t dt? When 2 comes out, we're going to use what? We're going to use x to the n dx equals x to the n plus 1 over n plus 1, right? N is just equal to 1, right? So we'll have 2t squared over 2. Do you see how this t is going to become t squared over 2? And this 2 comes from here. And that will be evaluated from 0 to t, where t we're going to plug in t final, so it just looks like this when we're done. All right? So now we can find the distance traveled by using the equation we just derived. And say that distance s that we're supposed to find is equal to 2 times, well, let's cancel the 2's, right? It's just t squared. all we need to do is plug in t squared. So t, at this point in time, I've erased it. It's 10.57, thanks. 10.57 seconds squared, and so that comes out to 111.8. But what are the units? It looks like they're seconds squared, but they're not. You have to be very careful. Once again, this 2 has units, right? Remember? If this 2 has units, we can cancel the numerical value of the 2, but this 2 does not have units. So the units of this remain behind. And I know I'm out of time, so I won't go through and show you, but because of the units that I should have included here from this 2, you end up with meters for your distance that the vehicle travels. I think it was a bus or something. Okay? All right, thank you for your patience. Have a good weekend, and I will see you next class.